Good morning, gang. All right, I'm going to close my door here and we're going to get started. I said good morning, didn't I? It's not morning anymore. Good afternoon, gang. So, first things first, a few little announcement-y bits. Of course, MAC2311, section 004. It's a lecture, and today is the 21st of September. So, announcements. Homework 4, I'll double check in a minute to make sure I remember to do this for your class, is due this Friday. Right, I extended. That's the homework that we opened up last week. Last Friday, I had that, I'm taking a course called AQ through the college, and they had a meeting that I had to attend, and it was supposed to be from like 12 to 1 or something, but it ended up being the whole damn day. So I wasn't able to record anything or do anything special for you. So of course, I imagine you guys have not finished homework 4 because it has lots of content that you're not ready for. We talked about that last week, and unfortunately, we're gonna have to push things back a little bit. That's okay. So homework 4 is due this Friday, and I'm today going to finish lecturing on the material that you need for that. I gave you the material, but I think there's 1 or 2 things in there that probably you didn't have or weren't quite ready for, just because you haven't seen enough examples. Homework 5, I just finished. It's up now, and this is going to be due next Friday, which, if you remember our discussion of exam 1 last week, is also the day of the test. So exam 1 is next Friday. Okay. This Friday, I will be opening up the study guide for exam 1. And you'll be able to work on homework 5 all the way up to the day of the test. So you're going to have a few things coming due on days that are not quite our normal days, and I just want to make sure you're aware of that. So homework 4 would normally have been due today, but since we haven't had time to work examples, it's not due today. It's going to be due this Friday. Just to give you some time, to be fair to you, because we didn't end up having a class meeting last Friday. Homework 5 is going to be on the next set of differentiation rules, the product and quotient rules, and that's going to be due next Friday. And then exam 1 is also going to be next Friday. So you're going to have a few things to learn over the next few days. Product quotient rule, and I'll also be teaching you how to take derivatives of trig functions. So those are kind of the new things you're going to learn before exam 1, which is next Friday. The chain rule, we're going to learn that after exam 1. So the chain rule is kind of a part of the middle third of the class, so you don't need to worry about that. I think that's all the announcement-y stuff. I'll talk more about the study guide this Friday when I release it, and I'll give you some instructions for the exam. But exam 1, I want to remind you, this is going to be on Canvas, proctored by HonorLock. So if you're not familiar with HonorLock, it's a Google Chrome extension that allows a proctor to monitor what you're doing. You'll need a good working webcam for that. It has to be a sufficient quality webcam that you can take a decent photo of your ID that is legible, readable. So if you don't have that at home, if you don't have access to that in your regular environment, please start making arrangements. If you're here in Gainesville, the college has 2 ways to help you out with that. You can use a computer in the library, but there's only a few computers there that have webcams. And it is possible that they would all be busy if you just showed up that morning and tried to take the test. The other option, we do have loaner laptops. So if you don't have a webcam, or your webcam's broken, or it's like 15 years old and it looks like a potato when it takes a picture, then you may want to consider either scheduling a computer at the library to use. I don't know if they let you reserve them, or scheduling a loaner laptop. And if you're interested in a loaner laptop, you'll need to contact me directly for that. And I can put the request in through Katie, our department chair, or you might be able to Google around and see a way to do it on your own. But I'd be happy to help with that. So this is kind of where we're going. And I just wanted to make sure we're all up to date with that. Are there any questions about this sort of announcement-y stuff? Okay. So I want to start today by doing some examples from homework 4, the sort of stuff that we would have done last Friday but didn't have time to do. And then I'm going to start on the material for homework 5. So let's do it. Let me pop open and take a look at your homework 4. I think actually I'll pop both of these. We'll bring both up, or is it going to fix one? Oh, yeah. Oh, no, that's Calc 2. Sorry. You guys are here. All right. So most of this homework 4 stuff should be familiar, of course. The first, 20 problems or so, I think is stuff that you have certainly all had plenty of practice with, and we did lots of these last week. 12 problems, maybe using the definition. Yeah, using the definition, using the definition. And then the cutoff was here at 22, right? And we did talk about this stuff last week, number 22. We talked about how the number e for us is defined by a certain limit. Does anybody recognize the appropriate limit here?
Wait, it was, I think, no, it's A.
It is, yeah, it's this first one, right? Because we set up the definition of the derivative for e to the x, and we notice that it comes out to e to the x times this limit. And then we said the definition of the number e is the number such that this limit comes out to 1. You can use a calculator here and get the obvious approximations there. So I want to start in on some of these things that we haven't really talked about. Before I do that, I'd also like to introduce, well, no, we're using all prime notation here, so I don't need to introduce the new notation yet. So let's just start talking about differentiation rules. So here's our formal beginning of chapter 3, although we did start it last week. Okay, so I'll remind you the rules that we know so far. Last week we proved the power rule, which says if f of x is like x to any power, then f primed of x is that power times x to that power minus 1. And this works no matter what the power is. It could be a nice number like x squared or x cubed, where the power is an integer, or it could be something weird like x to the square root of 3 or x to the pi. That all works great. It even works if the function is a constant. So some examples we've seen. You no longer need to use that big scary limit definition of the derivative. You can use this rule to differentiate x squared. So the derivative of x squared would be 2 times x to the 2 minus 1, which is 2 times x to the 1, or just 2x. Another simple example here would be like x to the square root of 3. If I wanted to differentiate that, x to the square root of 3, all primed, would be the square root of 3 times x raised to the square root of 3 minus 1. And there's no simplifying the square root of 3 minus 1. So we just leave it like that. Surprisingly, it also works for stuff like this. Can anybody think of a way I could apply this rule, the power rule, to a function like that? Yeah, I see there's something in chat there. Let's see. Good. So we begin by rewriting the inside as x to the negative 1. So this is x to the negative 1 all primed. Okay, and then if I follow my differentiation rule, so first I just did the algebra. I rewrote 1 over x as x to the negative first power. Now if I want to prime that, I follow this rule, because that is like x to the p. So that's negative 1 times x to the negative 1 minus 1. Negative 1 times x to the negative 2, which we could then rewrite as negative 1 over x squared. Okay, one last example. This might feel silly, but x to the 0 also follows this rule. This would be 0 times x to the 0 minus 1, or 0 times x to the negative 1. But 0 times anything is 0. So this is 0. And that leads us to our first new theorem of the day. In fact, it proves the theorem. If f of x equals c is a constant function, then f primed of x is identically 0. Right? X to the 0, that's really just 1. What this says is the derivative of 1, or any constant, is 0. And that we can reformulate down here as the statement of this theorem. There's another theorem that I want to show you before we get into more explicit examples, but first I'd like to take any questions on any of these, or the statement of this result down at the bottom. So any questions at all on our use of the power rule there? It would. Definitely applies to numbers like pi or e, because they are just constants. So the derivative of pi, 0. The derivative of e, 0. If it doesn't have any x's or any variables in it, its derivative is automatically 0, no matter how complicated the constant looks. Yeah, and that's a good question. One of my favorite kind of trick questions to put on early exams in this class is something like to calculate the derivative of e to the pi. And this is 0 because e is a constant, pi is a constant, e to the pi is a constant. So yeah, good question, Andrew.
It also applies to complex numbers, right? Like x to the I, right?
No. X to the I has
No?
x in it, right? If you had like I to the I, or 2i, or 5 minus 7i, those would all have derivative 0. But differentiation in complex numbers is actually different than differentiation in real numbers. Turns out most of the rules work the same, but a complex derivative is different than a real derivative. So for a touch of that, I would look at Merstand's Introduction to Complex Analysis. It's a good book that that's accessible at this level. Well, we're not going to talk about complex differentiability here. It's a slightly heavier topic than it might seem at the start. Oh, yeah, okay. So how would we deal with cube roots or other roots? We can look at a few more examples like this. So still just examples of the power rule. Can anybody help with Elisa's question? If I want to use the power rule to differentiate this function, how could I do that?
Put x to the 1/3.
Very good. So we first do some algebra. We first rewrite the cube root as a power. That's x to the 1/3 all primed. And now the power rule works beautifully. So I bring down the power, that's 1/3 times x raised to the 1/3 minus 1. And then we have to do a little bit of arithmetic up here. 1/3 minus 1. Okay, well, 1 is 3/3. So this is 1/3 minus 3/3 is negative 2/3. So this is 1/3 x to the negative 2/3. And all of these answers are the same answers that you would get if you used the limit definition. It's just a shortcut. It's a useful shortcut. Because those problems, if I wanted to differentiate this using the limit definition, would take the whole page. But yeah, this is the trick.
Would you put x to the negative 2/3 in the denominator?
So if we wanted to move that downstairs, it would become 1/3 times 1 over x to the positive 2/3. Or 1 over 3 times x to the 2/3, or if you're feeling fancy, you could write it as 1 over 3 times the cube root of x squared. So lots of different ways you could write this. But for the purposes of just calculating the derivative, I would accept this answer. Okay, so I do have a couple more theorems I want to share with you. And this next one, from certain perspectives, is sort of the most important. Derivatives play nice with addition and subtraction. And I'll be explicit about what I mean by play nice. So derivatives play nice with addition, subtraction, and multiplication by constants. They don't play nice with multiplication, division, but if you, and I'll be explicit about this, i.e., if you have a sum of two functions and you wish to prime that sum, you can just take the derivative of each individually and add them up. And the same is true for differences. So this is what I mean by plays nice with addition and subtraction. And then what we mean by plays nice with multiplication by constants is that if you have a constant c times your function, and you wish to differentiate that whole thing, the constant just comes along for the ride. The proofs of both of these are not at all hard. And I don't want to bore you with them. If you look on Paul's online math notes, and there's a link to it in the modules under the section on differentiation rules, you can find the proofs of each of these. But in this class, we're mostly concerned with building skills and being able to use the results. So instead of showing you the proof, I'd like to just show you some examples, and I'll bet you can figure out the proof on your own if you really want it. Okay, so let's find the derivative 2x cubed minus the square root of x, all primed. Well, according to this first part of the theorem, this is going to be the derivative of the first piece minus the derivative of the second piece. So I'm kind of thinking of 2x cubed as f and the square root of x as g. And what I have here is f minus g all primed. So that should be f primed minus g primed. Writing things out in the prime notation like this before you calculate the derivative is a hugely helpful thing to do. I strongly encourage that you solve your problems the way I'm solving them here in the examples. Okay, it won't just help with the calculation problems, it will also help with the more abstract concept problems. And now to each of these pieces, I can apply my power rule. Before I apply the power rule, I can use this rule for constant multiples that says the 2 will come out here. So this is 2 times the derivative of x cubed. So that's using the second part of my theorem. And then this guy I'll rewrite as x to the 1/2 because that's what the square root is. It's the 1/2 power. And now I'm to a place where I can use my power rule. Each of these that's left is just a power of x. So help me out. What's this first piece going to be? I have 2 times what when I differentiate the x cubed?
Three.
And what else?
Then x squared.
Good. Yeah, because x cubed will differentiate to 3x squared. And then this minus comes along. What about the x to the 1/2?
It's 1/2 x, and then
And up here would be 1/2 minus 1, right? What is 1/2 minus 1?
negative.
It's negative 1/2. So all together here, I've got 6x squared minus 1/2 times x to the 1/2. That's how I would write that. Now you could stop at this line. This line would be okay. But this is nicer. In fact, if you wanted to go a step further, you could write it like that. Okay, so these are important. The power rule and this result here are probably the 2 most important rules for differentiating functions you'll ever learn, in the sense that they're the ones you'll use more often than anything else. So questions, any questions on this example?
Can you explain the third line again? I'm having trouble with how you went from x cubed to 3x squared.
So the derivative of x cubed you bring down the power. So where did I write the power rule? It's on the other page. You bring down the power, and then you subtract 1 from the power.
Okay, thank you.
And the same is true for the other piece, the x to the 1/2 primed. We bring down the power, then we write x, and then we'll have the power minus 1. And 1/2 minus 1 happens to be negative 1/2, the same way 3 minus 1 happens to be 2. So that's the actual use of the power rule here. Okay. What else are we thinking? Any other questions on this one? Okay. So let's look at a problem or two from your homework then. We're ready to play with some of these. What's the derivative of the function in problem 23? Two to the 70. Yeah, good, Harris. 0. That's a constant. It's a big constant, but it's still just a constant. There's no x's. The graph of this function is a horizontal line, so its slope is always 0. 24. Same shit, right? E squared again is just a constant. 25. Good, 5.3. And in fact, you proved this as a part of an earlier exercise, that the derivative of a linear function is always just its slope. But you could also get this using the power rule. 5.3 times x to the 1. The 5.3 comes along for the ride. X to the 1 will differentiate to 1 times x to the 0. Let's do it. I'll show you how to do this with the power rule. So I know you've already done it, or I hope you've already done it using the definition. Now we can start making some connections. Now we'll look at a few harder problems. So this was homework 4, number 25. F primed, well, that's going to be that whole thing primed. Which would be 5.3x all primed plus 2.2 all primed, because the derivative plays nice with addition. And then the 5.3 pops out. X is x to the 1, so it's x to the 1 primed, plus the derivative of a constant is always 0. And then the derivative of x to the 1, you can follow your power rule. That should be 1 times x to the 1 minus 1 is 0. But x to the 0 is 1, so this is just 5.3 times 1. Not bad, right? Okay, I'm going to skip a few. Let's look at 32. Here, y is 6x squared plus 4x plus 8 all over the square root of x. This looks a little bit intimidating because it doesn't look like a bunch of addition and subtraction powers of x. But just like we did the 1 over x, we can use algebra to simplify this first. Ali, I'm not sure what you mean by 13. What's the question there?
20 said if you wanted to do. Oh, okay. She typed it.
Oh, okay, we want to go back and look at number 13? Yeah, we can do that in just a second. Let's finish this first though, okay? So y primed, that's all right, yeah, of course. So y primed here would be this whole thing primed. But I'm not in a place where I can differentiate this yet because I don't know how to take the derivative of something that looks like that. I need to have it be a sum of constants times powers of x. So before I do any calculus, I'm going to split this up. This is 6x squared over the square root of x plus 4x over the square root of x plus 8 over the square root of x, all primed. I'm going to let my cat in because he's scratching at the door. And now we're almost to something that we can differentiate. But first we have to use some algebra to clean these up and write them as just simple powers of x. So 6x squared over square root of x. How can I clean that up? Remember, square root of x is x to the 1/2. So this is 6 times x to the 2 minus 1/2 plus 4 times x to the 1 minus 1/2 plus 8 times x to the negative 1/2. And I still haven't done any calculus. Still just doing algebra. Are we comfy with why this term is what it is? I've got x squared upstairs and x to the 1/2 downstairs. And I also have this rule that x to the a over x to the b is x to the a minus b. Remember those algebra rules?
You just basically turned in the square root of x into 1/2.
Yep.
Right.
Yeah, exactly. I'm thinking of the square root of x downstairs as x to the 1/2, and then I'm using this rule. So x squared over x to the 1/2 should be x to the 2 minus 1/2. X over x to the 1/2 should be x to the 1 minus 1/2. And this guy is just 8 over the square root of x. That's 8 over x to the 1/2. That's just 8 times x to the negative 1/2. No x's upstairs. And I'm writing my prime out here because I haven't done the differentiation yet, right? I haven't actually done the calculus yet. I'm still just doing algebra. My next line, I'll clean up those powers, and then my last line, I'll take the derivative. So 2 minus 1/2 is 3/2. 1 minus 1/2 is 1/2. And this last guy just chilling. And I still have my prime outside because I still haven't taken the derivative. But in this next line, I will go ahead and take the derivative. So the 6 will come along for the ride. And then x to the 3/2, I'll bring that power down. And I'll subtract 1 from the power. And I'll just write it like this for now. The 4x to the 1/2, the 4 will come along for the ride. I'll bring the power down, and then I subtract 1 from the power, like that. And then this last piece, the 8 will come along for the ride. I'll bring the power down, and then I'll subtract 1 from the power. Okay. Now in my next line, I'm going to clean up the powers. And I'll also clean up the constants out front wherever I can. I think all of these will have some simplification. But first, any questions up to here? So we're all comfy with why this piece is the same as this piece? Why this piece is the same as this? And why this is the same as this, right? Any algebra questions you have about how we're simplifying those exponents or rewriting like this, I would like to deal with them now rather than later, because now is really the best time. remember, you can hold spacebar to unmute yourself like a walkie-talkie if you want to talk. Okay, so if there aren't questions, I'll go ahead and move to the last step here, which is just to simplify things. So 6 times 3 over 2. 6 is 2 times 3, so I can cancel the 2. And that will become 9. And then 3 halves minus 1, that's 3 halves minus 2 halves is 1 half. So this is 9x to the 1 half, that first piece. Plus 4 times 1 half, that's 2. And then x to the 1 half minus 1 is x raised to the negative 1 half. And lastly, 8 times negative 1 half, that's minus 4. And x to the negative 1 half minus 1 is x to the negative 3 halves. Okay, so this is the derivative. This is y prime. Any questions on this guy? Yeah, if all I ask for is find the derivative, then you can leave it like this. There are many different ways to write this. So I could, of course, put this back into radical notation as 9 times the square root of x plus 2 times 1 over the square root of x minus 4 times 1 over the square root of x cubed. And we could have a common denominator here. There's lots and lots of things we could do. But if you're just asked to calculate the derivative, it's fine to write it like this. That's a good question. Any other questions on this guy? All right, let's take a look at 1 or 2 more like this. Let's see, is there anything else like this that we should fiddle with right now? No, I think that's good. Okay, so then number 13, Ali wanted to go back and take a look at number 13, and then I'm going to talk to you guys about something called the product rule. Oof, 13 is a long problem. So here we're going to have to use the definition of the derivative to calculate g prime. I thought maybe we did this one last week, but if we didn't, that's okay. So in the interest of using class time well, Ali, let's do it like this. Give a thumbs up react if you would like to see the solution to number 13 here in class. All right, everybody knows how to use the reactions button. Look down on the bottom panel there at Zoom. If you'd like to see that solution here today, then go ahead and give a thumbs up react. Make sure it stays up for a few seconds so I can get a good tally. Okay, 1, 2, 4, 5, 6. Okay, I suppose that's worth doing. Let's go ahead and do it. It's an exercise from last week, but we can take a look-see here. I'm going to move a little bit quick because I do want to get to talking about the product rule at least today. So, g of t is 1 minus 3t over 2 plus t. We want to find g primed of t and its domain. First off, the domain of G is all real numbers except for -2. Because that, if you plug in -2, the bottom is 0. So that's -∞ to -2. union with -2 to infinity. So I know that G prime's domain will be a subset of this, right? G is definitely not differentiable at -2 because it's undefined at -2. And we talked about differentiability, right? The function has to be defined at that point, has to be continuous at that point, and has to be smooth at that point in order to be differentiable. So I don't expect G prime to have -2 in its domain, but it might have other restrictions also. So then G primed of t is the limit as h goes to 0, G of t plus h minus G of t over h. And this is going to be quite a large bit of computation. So I'm going to write the h downstairs as a 1 over h out front. G of t plus h is 1 minus 3 times t plus h over 2 plus t plus h minus G of t is 1 minus 3t over 2 plus t. So here's how we get started. The bracket box here is the numerator, and then the h downstairs I've written as multiplication by 1 over h, so I don't have to keep rewriting that huge fraction. I need a common denominator between these two pieces, and the only reasonable choice is this times this. So this will be lim h to 0, 1 over h times 1 minus 3 times t plus h over 2 plus t plus h times 2 plus t over 2 plus t. I'm giving a 2 plus t upstairs and downstairs here so that this guy will have this factor in his denominator. That's the factor he's missing. And then to the other piece, I will multiply by 2 plus t plus h over 2 plus t plus h to give him the factor that his denominator is missing. Now between those two pieces, I do have a common denominator. So I can write this as one big fraction whose denominator is 2 plus t plus h. I'm going to drop those parens there, times 2 plus t. And then upstairs is this times this minus this times this. So that's 1 minus 3t minus 3h times 2 plus t minus 1 minus 3t times 2 plus t plus h. So I distributed this 3 over that t plus h, and I dropped these parens here because there's nothing multiplying the t plus h. Now I need to distribute the 2 plus t over this trinomial and this 1 minus 3t over that trinomial. It's going to lead to a large expression. I'll also go ahead and put this h downstairs as a factor there. So I'll have my denominator h times 2 plus t plus h times 2 plus t. Upstairs, when I multiply this out, I'll distribute the 2 over all of these. So I'll have 2 minus 6t minus 6h. And now I'll distribute the t. So plus t times negative 3t squared plus t times negative 3h is minus 3ht. So I'm going to need a little more space. minus, and then I need to distribute all of this. So I'll put all of that in a big paren. When I multiply the 1 times 2 plus t plus h, I'll just get 2 plus t plus h. And now I distribute the minus 3t, I'll get minus 6t. Minus 3t times t is minus 3t squared. And minus 3t times h is minus 3th. And because I'm subtracting this whole chunk, I need to put this in these parens. Okay. Now I can distribute this negative over all these things. There are some like terms I can combine. I suppose we should do that first. So what about here? Combinable terms. 2, that's the only constant. Minus 6t plus t, so that's 2 minus 5t. So like this and this are like terms. Then minus 6h minus 3ht. And then over here, I'll have minus big paren. The 2 is the only constant. I've got plus t and minus 6t. That will make minus 5t. I've got, so that's this and this. Oh, I left off my t squared here. I've got a minus 3t squared here. Shit. Minus 3t squared plus. Yeah, this term I left off here. Tell you what. Let's do it like this. Make sure there aren't any mistakes in this flow. I don't want to make this any harder than it is. So I've got lim h to 0, 2, and then this 2 were minus 5t, minus 6h, minus 3t squared. There he is, minus 3ht, minus paren. All right, here we have the 2, and then minus 5t, that's where we were, plus h, minus 3t squared, minus 3th. All right. All of that over h times 2 plus t plus h times 2 plus t. And now we're almost there. We're going to distribute this negative, cancel anything that cancels upstairs, and then try to take our limit. So distributing this negative, this will be minus 2 plus 5t minus h plus 3t squared plus 3th all over h times 2 plus t plus h times 2 plus t. The 2's go. The minus 5t and the plus 5t goes. The minus 3t squared and the plus 3t squared go. Minus 3ht plus t3h, those go. All that appears to survive is this minus 6h and this minus h. I don't see anything else. So that will be lim h to 0 minus 7h over h times 2 plus t plus h times 2 plus t. And now we can cancel the h's, and sending h to 0 in negative 7 over 2 plus t plus h times 2 plus t, we get negative 7 over 2 plus t times 2 plus t, or negative 7 over 2 plus t quantity squared. It's a long problem. There's no denying it. It's a long problem.
So then when we put in the domain, it would just be negative infinity 2.
Well, so we got to think about domains, right? G primed of t is negative 7 over 2 plus t quantity squared. What's the domain of that function? Think back to your pre-calculus classes. How do you find the domain of a rational function? How can we piss this thing off?
Negative 2 is t.
Yeah, and that's it, right? Same as the original. The only place this is unhappy is if the bottom is 0. So the domain of G primed, it's the same as the domain of G. Negative infinity to negative 2, union with negative 2 to infinity. Everything except for negative 2. Okay, so that's a long ass problem. But the upshot is you take this definition, right? It's the same way we've been calculating all of our derivatives. It's just that this function happens to be a little bit complicated because it's a rational function. The top and bottom happen to not just be powers of t. Good news is, this is the last time I'm ever going to make you, aside from on the test, I will make you do this at least once on the test, but probably not with a function this complicated. Last time you'll ever have to use this limit to calculate a derivative. Before I move away from this, questions on any of these algebra steps? On any of the stuff we did to take this limit, which defines the derivative?
How did you take the limit when h is still in the denominator?
Oh, well, there is not a factor of h in the denominator anymore. I canceled the factor of h. Now there is an h right here. And when this h is 0, this factor just becomes 2 plus t. So having an h downstairs isn't a problem. It's having a factor of h downstairs that's a problem. This function is continuous when you plug in h equals 0. Because there is no factor that is equal to 0 when you plug in h equals 0. Does that make sense?
Yeah, that makes sense.
Cool, cool. Yeah, it's a reasonable concern, right? There's an h in the denominator. How can I send h to 0? Well, if you plug in 0 for this h, is the denominator 0? It's not. This piece doesn't go to 0. It goes to 2 plus t. So that's okay. Other questions about any of these steps? I've said it before, I'll say it one more time. There will be problems on the exam that require you to take a derivative using the limit definition of the derivative, this statement. It probably won't be as bad as this, but there will be something that requires you to work with this limit on the exam, maybe more than one thing. So if you've been Symbolabing or kind of hacking your way through those problems in the homework, it's essential that you practice them. I'll be putting at least one on the study guide so you can show me your work on that and we can talk about it and make sure it's okay. I don't want this to hurt anybody, but you do need to practice it. If you don't practice it, it will bite you in the ass. Okay. Last call for questions on any of these steps. All right, then I got good news for y'all. The reason that's the last time you have to do that is I'm about to show you two new rules. Right, like you've got your power rule that keeps you from ever having to differentiate power functions with those limits again. You recall from last time we had this theorem on exponential functions that b to the x primed is always b to the x times the natural log of b. Our next theorem, there's two rules here, product and quotient rules. This says that f of x times g of x primed. It's not as nice as just f prime times g primed. I said that the derivative plays nice with addition, subtraction, and multiplication by constants. So here, if these are not both constant, if one of these is not a constant function, then what you need is the product rule, which looks like this. You differentiate one function at a time. So you differentiate the first function and you leave the second alone. And then you add that to what you get when you leave the first function alone and differentiate the second. This is called the product rule. And if there's a product rule, you can guess that there is a quotient rule. Again, you can't just differentiate the top and the bottom separately. That does not work. But what does work, the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. This is called the quotient rule. The quotient rule is a little bit complicated looking. In order to remember it, I have a mnemonic. Some people like this, some don't. It's low d high, the bottom times the derivative of the top, minus high d low, the top times the derivative of the bottom, over low low. For some reason, this works for me, and it's worked for a lot of my friends and students in the past. So if you're having trouble remembering the quotient rule, remember this mnemonic, low d high minus high d low over low low. For some reason, it just rings in the brain and stays there. These things will rescue you from a lot of nasty derivatives, like, for example, the one we just took. Let's revisit it. g of t there was 1 minus 3t over 2 plus t.
And then again, we could just like use the product rule and like chain rule later, of course.
You would need the chain rule to get around the quotient rule. So you need the product rule combined with the chain rule. And we won't learn the chain rule until after exam 1.
Yeah, because quotient CC the most annoying rule.
It is, yeah. So according to the quotient rule, the derivative of this function should be the bottom times the derivative of the top. So that's 2 plus t times 1 minus 3t primed minus the top, which is 1 minus 3t times the derivative of the bottom. So 2 plus t primed over 2 plus t squared. And already it's looking good because when we did our calculation, we got a 2 plus t squared downstairs. Let's carry out the rest of it. 2 plus t is just 2 plus t. 1 minus 3t primed. What is that? What is the derivative of the top? You might come off to the side here. 1 minus 3t primed. What is that? This is a power rule thing, right? The 1 will differentiate to 0, and minus 3t will differentiate to minus 3. And then 2 plus t primed, this is also a power rule. The 2 will differentiate to 0, and the t will differentiate to 1. So this is 2 plus t times 1 minus 3t primed, that's negative 3, minus 1 minus 3t times 2 plus t primed is 1. And then we'll distribute upstairs and see what we get. 2 times negative 3 is negative 6. T times negative 3 is minus 3t. Minus, distribute here, minus 1, and then plus 3t over 2 plus t squared. The minus 3t and plus 3t go. Negative 6 minus 1 is negative 7. Hey, we did it right. Now, I don't know about you. I would rather do this than the page of work we had to do to get the other guy. So yes, the quotient rule is a little bit annoying. I'll concede that. But it's a whole lot less annoying than calculating the derivative using the definition.
So can we use that instead?
So here's what I said last week when I was talking about this homework is that you can use these rules, the power rule, quotient rule, product rule, on any problem unless it says use the definition of the derivative. So problems 1 through 21, I'll say use the definition of the derivative. That's to get you practice at using those limits. And it's important. The limit is also how we determine whether a function is or isn't differentiable. It's how we answer abstract questions about the derivative. It's how we understand what the derivative is. But once we've covered this section, which now we have, you're free to use this rule on any problem that doesn't explicitly tell you not to.
Gotcha.
So all the problems after problem 21 in homework 4, and all of the problems in homework 5. So no more do we need to use that. As long as you've finished through problem 21 in homework 4, you never have to touch that again, aside from on the test. But please do, in working problems 1 through 21, use the actual limit definition of the derivative. Otherwise, you're kind of shooting yourself in the foot, because there will be questions on the test that require it, and you need to practice in order to get good at it. I know it's not fun, but it is worth doing. Okay, let's see some more practice with product and quotient rules though. Now that we've got these dope new tools, let's use them. There are some things that we could not differentiate before that we can differentiate now. One of my favorite examples is this guy. X times e to the x, that's definitely a product. So I will use my product rule. The derivative of x e to the x, well, first I differentiate the x, so this is going to be x primed, and I leave the other guy alone. And then I add that to what I get when I leave the first guy alone and differentiate the second guy. So this is the product rule. Does everybody see it? F prime times g plus f times g prime. I didn't label them like that because the whole function here is called f, but that's the pattern. Now the derivative of x is 1. So that first piece is 1 times e to the x. X is just x, and the derivative of e to the x is e to the x. And here, if we factor an e to the x out, we can write this more neatly as e to the x times 1 plus x. Nifty, right? How am I doing on time? 1:39. Let's see, this is a 12:30 to 1:45, right? Yeah, so we're still good. I'd like to show you one more if there are not any questions on this, but if there are questions on this, I'd like to talk about them. Any questions about any one of these steps? Okay, if not, then for my last problem here, let's find the equation of the tangent line to f of x equals x e to the negative x at x equals 0. So remember, to find the equation of the tangent line, you need two things. You need a point and the slope, just like to find the equation of any line. The point is going to be the point on the graph of f of x at x equals 0. So that's 0, comma, f of 0. And f of 0, if you plug 0 in here, you get 0 times e to the negative 0. That's 0 times 1, which is 0. So this is, the point is 0, comma 0. And then for the slope of the tangent line, you always need the derivative. So I need to calculate f primed of x, which is the derivative of x e to the negative x. And at a glance, it looks like we're in trouble because I don't know how to differentiate e to the negative x. I just know how to differentiate e to the x. So first I'm going to need some algebra. How can I rewrite x times e to the negative x as something that I know how to differentiate? Or how can I rewrite e to the negative x?
1 over e to the x.
Good. And then x times 1 over e to the x, that's x over e to the x. So that's really what I'm trying to differentiate. And now I can apply my quotient rule to this because I know how to differentiate the top, I know how to differentiate the bottom. So let's do it. I know this is going to be the bottom times the derivative of the top, that's low d high, so that's e to the x times the derivative of x, minus high d low, that's x times the derivative of e to the x, over low, e to the x, all squared. Now, we go in and each one of those derivative pieces we work out. This is e to the x times the derivative of x is 1. Minus x times the derivative of e to the x is e to the x. And downstairs, e to the x squared, that's e to the 2x. All right, here I'm using a few things. I'm using the fact that the derivative of x is 1. The derivative of e to the x is e to the x. And I'm using this rule for powers that says a to the b all to the c is a to the b times c. So that last one isn't a differentiation rule, it's an algebra rule. But that's what I'm using to rewrite e to the x all squared as e to the 2x. And then if you want, you can clean this up. This is e to the x minus x e to the x over e to the 2x. So to get my slope, I need to do one last thing. I have my formula for f primed. It's this. If I want the slope of the tangent line at this point, what do I do with this?
Plug in 0.
Very good. I plug in the x value at that point. So this implies that the slope of the tangent line is f primed of 0, which is e to the 0 minus 0 times e to the 0 all over e to the 2 times 0. E to the 0 is 1 minus 0 times 1 is still 1. And then downstairs, e to the 2 times 0 is also e to the 0, which is 1. So this is just 1. Therefore, my tangent line it's y minus y0, which is 0, equals m, which is 1, times x minus x0, which is 0. In other words, it's just y equals x. Right here, I'm using the point slope form of a line. Y minus y0 equals m times x minus x0, just like we did in all of these other ones. Last thing I want to do before I sign out for the day is to take a look at the graph of these two functions, x e to the negative x and x e to the x, because they're both pretty cool. First, any questions on the derivative calculation? This is the new thing for today. All right, let's take a look at those graphs. Here is x e to the negative x. Pretty cool, right? So we found the slope of the tangent line right here at 0. The tangent line we discovered was y equals x. There he is. And the derivative itself looks like this. So first, here's the function we just worked with. Here's his tangent line at 0. And then the derivative of that function is shown in green. And you'll notice that something cool happened right here. The original function had a local max. And at that local max, the derivative was equal to 0. So as we move out of chapter 3 and into chapter 4, we're going to start talking a lot more about how to find maxes and mins. And you'll notice that this connection with the derivative being 0, where the original has a max or a min, is consistent. The other function we looked at was x e to the x, which is very similar looking. And he has a local min right here at -1. And if you graph the derivative, you'll see the derivative has an x-intercept at -1. But for now, what I want you guys to be doing is just practicing with the mechanics of these differentiation rules. That's the most important stuff for exam 1, that you can take derivatives. With the power rule and the rule that says derivatives play nice with addition, subtraction, and multiplication by constants, you can now differentiate any polynomial or any linear combination of power functions. With the quotient and product rules, you can now differentiate like any exponential times any polynomial, any rational function, or any rational combination of exponentials and polynomials. That's a big family of functions. That's a lot of stuff. The last thing we're going to learn, and we're going to be learning this after exam 1, is what's called the chain rule. And the chain rule is a trick for differentiating composite functions. Like rather than differentiating the square root of x, differentiating the square root of 5x squared minus 2e to the x. We're also going to talk about derivatives of trig functions. So they're a little bit special. They don't require any rules, but the limits that you need to calculate the derivatives of trig functions are kind of complicated. That's what we're going to talk about on Wednesday. So on Wednesday, I'm going to show you how to differentiate sine, how to differentiate cosine, secant, tangent, cotangent, and cosecant. And then on Friday, we'll put that together with what we've been doing and differentiate rational or algebraic combinations of polynomials, exponentials, and trig functions. And with that, we will be ready for exam 1. So on Friday, after we talk about the derivatives of trig functions and how to combine them with these other things, I will release the study guide for test 1. Monday of next week, I will show you the chain rule, which is not going to be on test 1. And then we'll start reviewing for test 1. Wednesday will be all review for test 1. And then Friday, during what would normally be our class time, we will go ahead and have exam 1. And I'll post lots of instructions. When I do post those instructions for exam 1, please read them carefully. It's important you follow them exactly. And also make sure that you have something set up that will allow you to use honor lock. So I recommend checking to make sure your system is capable of using honor lock. If it doesn't meet the minimum requirements, if your webcam isn't working or you don't have a webcam, please reach out to me or reach out to someone in the library to make sure that you'll have access to a computer with a webcam next Friday. Okay? Any questions for me before we sign out for the day?
No, thank you.
Alrighty then, I will have my normal office hour this afternoon. I think this beard is about 1.5 years old, but I don't remember. I shaved it off last year at one point, somewhere around there. All right, have a good afternoon, guys. If you want to come by office hours, I'll see you there. Otherwise, I'll see you on Wednesday.
Thank you.